You think you understand time because you can read a clock or feel yourself getting older. But that feeling isn't time, it's just how your brain keeps track of change. Your memory gives you a sense of before and after, and you call that time passing. But physics doesn't care about your memory. Physics doesn't even care if you exist. So, when we ask what time actually is, we need to be very careful not to confuse our psychological experience with what is really happening in nature. Here's a strange observation that should bother you. If you take two identical clocks perfectly synchronized, and you put one on an airplane flying around the world while the other stays on the ground, when the airplane lands, the two clocks no longer agree. The one that traveled is behind. It didn't malfunction. It didn't slow down mechanically. It measured less time, not because of some technical error, but because less time actually passed for it. How is that possible? If time is just what clocks measure, and both clocks are identical, why would they disagree? And more disturbingly, which one is right? Subscribe and like for more videos that explain what's really happening beneath the surface. Because what we're about to uncover challenges everything you thought you knew about the simplest thing in your life, time itself. Let's start with what we actually mean when we say time. You might say time is duration or sequence, or the thing that keeps everything from happening at once. But those are just words describing your experience. In physics, we need something more precise. And here's what Feynman would tell you. Time is what we measure with a clock. That sounds circular, but it's actually the only honest definition. We don't know what time is in some deep philosophical sense. We only know how to measure it, and we call that measurement time. Now, what makes a good clock? It needs to be periodic, it needs to repeat the same process over and over in a way that we can count. The earth rotating is a clock. Your heartbeat is a clock. An atom vibrating is a clock. But here's the critical question. How do we know these clocks are any good? How do we know they're measuring time accurately and not speeding up or slowing down? The only way to check a clock is to compare it to another clock. If two clocks agree, we gain confidence. If many clocks agree, we call it agreement time. But notice what we've done. We've defined time by consensus among our measuring devices. We have no external standard to compare against. There's no cosmic clock ticking away the true time that we're trying to approximate. There's just a collection of physical processes that we've agreed to use as references, and we call their behavior time. This seems fine until you do something strange, like put one clock on an airplane, or send one clock up a mountain, or accelerate one clock to high speed. Then the clocks disagree. And that disagreement isn't measurement error, it's nature telling you something profound. There is no universal time. There's no single clock that all observers agree on. Time is not absolute. Let's do a thought experiment. Imagine you're on a train moving at constant speed, and I'm standing on the platform. You have a clock, I have a clock. From your perspective, sitting on the train, you are stationary. The train is your universe. You can bounce a ball, pour a cup of coffee, do anything you could do if the train were stopped, and it works exactly the same way. There's no experiment you can do inside the train without looking outside that tells you you're moving. Motion is relative. You can only say you're moving relative to me on the platform. Now, here's where it gets interesting. You decide to measure the speed of light. You shine a flashlight from the back of the train to the front and clock how long the light takes to travel the distance. Standing on the platform, watch you do this experiment as the train passes by. From my perspective, The light is not just traveling from the back to the front of the train, it is also traveling forward with the train's motion. So from my perspective, the light has farther to travel than it does from your perspective. Common sense says we should measure different speeds for the light. If the light travels farther in my frame than in yours, but we measure the same time interval, then I should measure a faster speed. Or if we measure different time intervals, then the speeds could match. But here's the staggering experimental fact. We both measure exactly the same speed for light. Not approximately the same. Exactly the same, to every decimal place we can measure. This is not a guess. This is not a theory waiting to be refined. This is what happens. The Michelson-Morley experiment in 1887 was the first to show this convincingly, and every subsequent experiment has confirmed it with increasing precision. Light moves at the same speed for all observers, regardless of their motion. That speed is approximately 300,000 kilometers per second, and it's the same whether you're moving toward the source, away from it, or standing still relative to it. Now, if you accept that fact, and you must, because nature enforces it relentlessly, then something has to give. If the light travels different distances in our two frames, but we both measure the same speed, then we cannot be measuring the same time intervals. Your clock and my clock cannot agree. Time must be different for you on the train than for me on the platform. This is not a defect in our clocks. This is not about mechanics or engineering. This is what time actually does. Time is not universal. Time is relative. What you call 1 second and what I call 1 second are different durations when we're moving relative to each other. Let's make this concrete. Imagine the train is moving very fast, not the speed of everyday trains, but a significant fraction of the speed of light. Let's say have the speed of light, which is 150,000 kilometers per second. Now, the effects become noticeable. If you, on the train, experience 1 hour passing, I, on the platform, experience more than 1 hour passing. Not because your clock is broken, but because less time actually passes for you. You age less. Your heart beats fewer times. Chemical reactions in your body occur fewer times. Every physical process that constitutes your existence runs slow from my perspective. But here's the kicker. From your perspective, sitting on the train, you experience time normally. You don't feel sluggish. Your clock doesn't appear to run slow. Everything in your frame is consistent. It's only when we compare our clocks that we discover the disagreement. And the disagreement is symmetric. From your perspective, my clock is the one running slow, because I'm the one moving relative to you. Motion is relative, remember. There's no absolute sense in which one of us is moving and the other is stationary. Now you might ask, when the train stops and we compare clocks directly, which clock will be behind? The answer is whoever accelerated. The twin who stays on Earth and the twin who travels in a spaceship and returns the traveling twin is younger. Not because of the motion during the constant speed portion of the trip, but because of the acceleration at the turnaround. Acceleration breaks the symmetry. It's not relative. You can tell if you're accelerating without looking outside, because acceleration has physical effects. You feel forces. Things fall over. Blood rushes to one side of your body. This is the famous twin paradox, but it's not actually a paradox once you understand that time is relative and that acceleration matters. The traveling twin ages less because less time passes in their frame during the journey. When they return, they're younger. This isn't science fiction. This has been measured with atomic clocks on airplanes, exactly as I described at the start. The effect is tiny at airplane speeds, nanoseconds of difference, but it's real, measurable, and exactly what Einstein's special relativity predicts. So what is time, really? Time is what clocks measure, and what clocks measure depends on their motion through space. Space and time are not separate, independent things. They're woven together into what physicists call spacetime. When you move through space, you're also moving through time, and the faster you move through space, the slower you move through time, from the perspective of someone who's not moving with you. Here's the deep insight that Feynman would emphasize. Nature doesn't care about your intuition. Your brain evolved to survive on the African savanna, where velocities are slow and time feels absolute. But nature isn't constrained by how your brain works. At high speeds, or strong gravitational fields, nature reveals that time is flexible. It dilates. It's relative. And there's nothing you can do about it except accept what the experiments tell you. Let me give you one more way to think about this. Imagine you're walking across a field, heading north. You can measure your progress by how far north you've traveled. Now imagine you turn slightly to the east while still walking forward. You're still covering the same distance with each step. But now some of that distance is going north and some is going east. The more you turn east, the less progress you make north, even though you're walking at the same speed. Space-time works like that. You're always moving through space-time at a fixed speed, the speed of light, in a sense. But you can redirect your motion. The more you move through space, the less you move through time. The less you move through space, meaning, the slower you are, the more you move through time. Something moving at the speed of light, like a photon, doesn't move through time at all from its own perspective. If a photon could have a clock, it would measure zero elapsed time for its entire journey, no matter how far it travels. From the photon's perspective, it's emitted and absorbed in the same instant. This is why light doesn't age. A photon emitted from a distant galaxy billions of years ago experiences no time. The universe begins and ends in the same moment for the photon. From our perspective, billions of years passed. From the photon's perspective, nothing passed at all. That's not metaphor. That's what the physics says happens. Now, why does this matter? Why should you care that time is relative? Because it tells you something fundamental about the structure of reality. Reality is not made of objects existing in space, with time as some external parameter ticking away in the background. Reality is made of events in spacetime. An event is something that happens at a particular place and a particular time. And different observers, moving relative to each other, will disagree about when and where events happen. They'll disagree about whether two events are simultaneous. They'll disagree about the duration between events. But there's a deeper structure, the space-time interval between events, that all observers agree on. That's the invariant. That's what's real. Your intuition about time is wrong because your intuition was built for a world where speeds are slow compared to light. In that world, time seems absolute, and space seems absolute, and you can separate them cleanly. But that's an illusion created by limited experience. At high speeds, or near massive objects where gravity is strong because gravity also warps time, the illusion breaks down. Time bends. It stretches, it slows. And the only way to understand that is to let go of your intuition and trust what the experiments tell you. Feynman would tell you to be honest about this. We don't have a satisfying answer to why time behaves this way. We just know that it does. We have equations, the Lorentz transformations, Einstein's field equations, that describe how time behaves with incredible precision. Those equations make predictions. We test the predictions. The predictions are confirmed. That's how science works. We describe how nature behaves. We don't explain why nature chose to behave that way. Maybe there's a deeper explanation. Maybe there isn't. But the behavior itself is not up for debate. Time is relative. That's a fact about the world. So the next time you glance at a clock and feel time passing, remember, that's just your brain's way of organizing experience. Time itself doesn't pass. Events happen. Change occurs. And different observers, moving through space-time in different ways, measure different durations between the same events. You're not watching time flow. You're existing in space-time, moving through it, experiencing it from your particular frame of reference. And that frame is no more special, no more correct, than anyone else's. Time is what happens when you measure it. And what you measure depends on how you're moving. That's the truth about time, as best as physics can tell you. It's strange. It's counterintuitive. And it's absolutely, demonstrably real.